Okay, I apologize for that. 8 years ago, whenever I would think about determinants, and my daughter was listening to that song, yeah. So, anyway, determinants. Very handy if you are somebody who has to take differential equations or Calc 3. So, any engineering students out there, you have to know determinants. Alrighty, so just a little bit for you to understand. So a determinant of a matrix has to be a square matrix, n by n, is a number in its field. Okay, and that's for us usually R, right? But it can be other fields. It's a number that can quickly tell you whether the matrix is invertible or not, which is handy, as well as open up all of eigenvalue, eigenvector theory, and find volumes of parallel pipeds and areas of parallelograms, all kinds of interesting things that get used. So let's just hit the definition. The determinant of a matrix is the sum of -1 raised to the I plus j, where these, think of A as being a matrix that has a bunch of entries, Aij, right? So what you do is you get the sum expanding along some row or some column of that matrix. You take the entries in that row or that column and multiply them by -1 raised to the I plus j power, and multiply it by something, well, that is called the determinant of the minor matrix. Yeah, another way of writing determinant of a matrix is to kind of put absolute value signs around it. And again, that definition is this sum. So for example, well, for 2 by 2s, it's nice and easy. If you have 1, 2, 3, 4, the determinant of that is just 1 times 4 minus 3 times 2. So the product of the diagonal minus the product of the counter diagonal. So that's 4 minus 6, and -2. As long as you've got your order of operations working, right, you'll be having no problems. If it's a 3 by 3, so if we have, let's see, if B is equal to a matrix with 1, 2, 3, 4, 5, 6, 7, 8, 9, then our approach is to expand along any row or column, and I will choose the one with lowest values and use this formula. So that's going to look like this one, first a -1 raised to the 1 plus 1 power, which is 2, multiplied by that number 1, multiplied by the determinant of Mij, the minor matrix associated with A11, is this little matrix here, which you get by crossing out the column and the row that A11 is sitting in. So I would put 5, 6, 8, 9 in here, and I'll be taking that 2 by 2's determinant soon. This is an equal sign, sorry. Okay, plus summing -1 raised to the, so now I'm on this term, that's the 1, 2 term, 1 plus 2, that's going to be 3. -1 to the 3 is going to give me a -1 power there, times that element 2, times it's the determinant of its minor. What's its minor? If you throw out the row and the column the 2 are in, what are you left with? 4, 7, 6, 9. Okay, plus, summing along, -1 raised to the, now we're in this term, that's the 1, 3 term, so that's 1 plus 3 power, or 4. That's going to make that an even quantity. in here, and so negative 1 to the 4th is going to be a positive, times that entry, which is the 3, times its minor. So if you cross out that row and that column, you're left with 4, 5, 7, 8. What does this turn out to be equal to? I wrote this example. Not this time. Oh well, let's do it now. So we end up getting 1 times this determinant. What's that? That's 45 minus 48 minus, because that's negative 1 to the 3rd power, 2 times the quantity 36 minus 42 plus negative 1 to the 4th power is a positive 1 times 3 times this determinant, which is 32 minus 35. And so what does that equal? What is that equal to? Well, let's see. That's a negative 3 minus a 2 times, that's a negative 6. Right? Yep. Plus 3 times, that's another negative 3. And so we end up getting plus 12 minus 9. Ooh, look at that. Turns out to be equal to 0. The determinant of A equaling 0, we're going to see, means that this is what we would call a singular matrix. And by that, we mean it's a rare bird, and it actually will turn out to not be invertible. But the proof of that is coming up. All right, so once you know how to take determinants of a 3 by 3, this definition of determinant will expand to 4 by 4s. Then you expand along any row or column using this property. All right, so some important things you need to realize. First of all, elementary matrices have some pretty nice determinants. So let's see. If EK switches 2 rows, okay? If that's an elementary matrix, that multiplying on the left by it switches 2 rows. For example, in the 3 by 3 case, what would that look like? Let's say if we wanted to talk about the equivalent of taking row 2 and row 3 and switching them. Remember how we construct the elementary matrix? We take an identity matrix and apply that to it. So this transformation would leave row 1 all alone in the identity matrix, but would switch rows 2 and 3. So we'd have a 0, 0, 1, and a 0, 1, 0. So this is an example of such a thing. Well, what's its determinant? So EK here has determinant, well, let's see, you can expand along this first row or this first column. Let's go with the first column this time, just so you have some practice with that. So that would be equal to negative 1 raised to the 1 plus 1 power, because that's the 1, 1 position, times that entry, times this determinant of this minor, 0, 1, 1, 0, plus a negative 1 in this position, that's the 2, 1 position, so it's 2 plus 1 power, under negative 1, which is going to make that minus the entry. Oh, the entry is 0. So who cares about whatever else? Plus last, oh yeah, that's another 0. So we end up caring about this one, we don't care about that one. We love lots of zeros when we have to take a determinant, right? What's this? This is a 1 times a 1 times a 0 minus 1. So its determinant is negative 1. That's just an example. But it is true in general. Not much of a proof, but there you go. So if you're switching 2 rows, the determinant equals a negative 1. Okay. If your elementary matrix, let's say, multiplies row I by some alpha not equal to 0. So, for example, well, let's see what that would look like. Let's say the alpha not equal to 0 we're going to take here is, how about a -5? Right? So if I only have a 2 by 2 case, that would look like 1, 0. Let's see. Got ahead of myself there, sorry. Yeah, so if I'm multiplying the second row by a 5, a -5, I would get this, right? So there's that matrix, its determinant. So straight lines around a matrix mean we're taking the determinant. Okay, brackets mean it's just, we're talking about what's in the matrix itself. Straight lines around it means you're taking the determinant. So that is equal to a -5. Yes, that extends to larger cases. If your elementary matrix is simulating multiplying a row by some alpha, then its determinant is that alpha, non-zero. This one was also non-zero. Last, elementary matrix, what's left? Oh yes. So if your elementary matrix, what does it do? Accomplishes that most handy of row operations. New row I is equal to old row I plus alpha times row J, where alpha is not equal to 0 and J is not equal to I. That one. An example. Let's say that you had wanted to do this with a specific example. Let's say we're going to take new row 3 is going to be equal to old row 3 plus pi times row 2, say. Okay? What would that look like? Well, let's see. Pi times row 2. Row 2 normally looks like this, right? Oh, and it's still going to look like that, right? Because we're only going to transform row 3. There's row 2. If you multiply that by pi and that to row 3, you're going to get this. What's that determinant? Sorry if the song is in your mind because of the word, but anyway. So if I want to say the determinant of this, let me erase the brackets. Now we can just have the straight lines. Oh, what happened there? Oh, brilliant. Just flip that. Okay. Oh. Gymnastic interlude was brought to you by some physics I don't understand. All right, so what is this determinant? Well, let's see. It's going to be a 1 times the determinant of this minor plus a bunch of zeros. And so that'll be equal to 1 minus 0. Oh, look at that. The 0 times the pi, or whatever that alpha was, that's just going to go away. Oh, sorry, not 1 minus 0 is still 1, excuse me. So if you're using this row operation, as nasty as it is, it doesn't change the determinant of the identity matrix. The determinant of such a matrix that will generalize is just going to be a 1. All right. Now, here is a property of determinants that's probably the most important property you're going to be using again and again and again. And it's this, that the determinant of a product of matrices, and I can see, you could probably see why we want to get there. But remember when we take these elementary matrices, we multiply them up, right? And that puts our matrix in row reduced echelon form, right? So, well, the determinant of a product of them turns out to be equal to the product of each one's determinant. This is what we're going to prove right here. Did I say proof? Let me show you the proof. Here's the proof. On page 175 of your book, down at the bottom, proofs of theorem 3 and 6. They prove theorem 3 about products of determinants of products of elementary matrices, and then they use that to make the general theorem true. Just run the song and read that, and then you'll have that proof. Okay, so let's talk about using that property, which is this, that the determinant of a product of two matrices is equal to the product of their determinants. So handy. All right. Well, this key property of determinants allows us to do a bunch of things. For example, this property. Property 1. If A is invertible, the determinant of A does not equal to 0. Okay, why is that true? Here's the proof. A times A inverse, we said A was invertible, so A inverse exists. That's got to be equal to the identity matrix. Oh, right. What should be the determinant of the identity matrix? 1, 1, 1, and a bunch of zeros otherwise, everywhere. You expand along the first row, that's going to look like -1 to the 1 plus 1, multiplied by 1, times the determinant of the matrix that's n minus 1 by n minus 1. And that will be the determinant of its minor times this factor, so on and so forth. Turns out very nicely that this will always add up to just a 1. Not a great proof. Here's the first, or the second case, right? That's a 1. Its determinant is 1 times that one, which is 1, and so on. So the determinant of an identity matrix is equal to 1. So now we have the determinant of A times A inverse has got to be equal to a 1. We just took the determinant of both sides, right? Assuming the key property, so by our star property here, this looks like the determinant of A times the determinant of A inverse is equal to a 1. Right there. That tells you the determinant of A cannot be equal to 0. Okay? Property 2, also from this line, tells you that the determinant of A inverse is equal to 1 over the determinant of A. How did I get that? Again, if A is invertible, then we have A times A inverse is equal to identity. Take the determinant of both sides. We get the product of those two is equal to 1. So the determinant of A inverse is equal to 1 over the determinant of A. Why are we necessarily allowed to divide by determinant of A? Because it's non-zero. Right. You should be able to fill in the blanks on that one. That would be a great test question, don't you think? All right. So, no, we didn't prove the star property, but we did prove two others from it. Yeah, little ones. You should be able to do those. Let's see, what else? Oh yeah, how about this one? Property 3. I think that's enough. Yes, we'll stop now. Thanks.